So we're really happy today to have Arianna Gleason here. She's doing some of the cutting-edge work on shock physics and behavior of materials under high pressure and temperature from an experimental point of view. She got her PhD from Berkeley with Ray Johnlow, and she did her postdoc with Wendy Mao at Stanford. And she's currently at Los Alamos National Lab in the Shock and Detonation Physics group. And she's a, let's see, currently her title there is Distinguished Postdoctoral Scholar and Visiting Scholar at Stanford, as well as at Los Alamos. And she was a Director's Fellow at Los Alamos until 2015. She has a very impressive resume. She's got her PhD in 2010, but she's already published 26 papers, and many of those are in science and various nature journals. She's worked on a variety of different materials and different problems, and she's going to give an overview today, so you'll see some of the different things that she's been working on in her talk today on ultra-fast X-ray studies on the dynamics of transitions in planetary materials. So unfortunately, she has a busy and limited schedule today, so please come to lunch afterwards, and if you're not already on the schedule, to talk to her. And I think we're in for a very interesting talk. So,
thank you. Thank you so much for that introduction. My name is Arianna Gleason from Los Alamos National Lab and also at Stanford University. And today it is my pleasure to share with you a few of the new exciting research and experimental developments that have been going on coupling ultra-fast X-ray probes and laser-driven shock techniques as applied to planetary materials. Before I begin, I want to acknowledge my collaborators, in particular Cindy Bolme from Los Alamos National Lab, Wendy Mao from Stanford University and SLAC, and certainly the entire experimental and beamline staff at the LINAC Coherent Light Source. So a shock wave is the fastest mechanical loading we can achieve, providing a nearly instantaneous change in thermodynamic conditions, from which material-based dynamics, controlling changes in state and physical properties, can be measured. Okay? So today we're going to learn about or investigate coupling shock wave compression techniques and ultra-fast X-ray probes to give us an atom-eye view into how phase transitions take place, what is their time scale, and basically the kinetics of some important phase transitions, not only in Earth or planetary type interior and impact scenarios, but we could think of going from the atomic scale and really coupling mesoscale components of real materials with how we understand their transformation processes. And we're going to essentially take a tour through the Earth. So we'll begin by looking at some materials that are most common at the Earth's crust and upper mantle, so SiO2. We'll look at phase transitions in water, in ice, and then we'll move on to the mantle and look at some transitions, in particular spin transitions coupled with structural transitions in iron-bearing silicates. And then finally we'll move on to my favorite, the core, and look at some transitions in iron and iron alloys. To begin, we must have an extremely bright, brilliant X-ray probe to actually visualize these transitions as they take place on the material timescale. And to do that, we've used the LINAC Coherent Light Source, the X-ray free electron laser that is there. It is essentially several kilometers long, and this is a picture of SLAC, and the experiments that will be conducted take place at the FAR Experimental Hall. And the benefit is really several things. This X-ray free electron laser, it's the first in the United States of its kind to operate in the hard X-ray regime, and the brilliance, the number of photons, 10 to the 9, a billion times brighter than any synchrotron source to date, okay? Operates between 4 and about, now it's about 11.5 keV. It's tunable, okay? And the pulse width, the temporal width, is shorter than even a phonon period, right? So we're talking about, say, 10 to 60 femtoseconds. So I am taking a snapshot of my material as it's undergoing this transition, okay? Now, just as an aside, we can plot peak brightness. So here we are, LCLS. Later this year, the European XFEL will also come online, and it will provide an even more brilliant source. And my understanding is that in a year from that, 2018, 2019, we'll also have LCLS2, which will then go beyond. So it's a continued evolution, technical advancement in X-ray free electron laser technology. Now this is then coupled with a dynamic driver. So at the matter and extreme conditions hutch at LCLS, we are afforded the opportunity of two types of shock drivers. So we have a short pulse laser and a long pulse laser. So today we're going to talk about the long pulse laser shock compression. So this is a large laser that essentially is like a rocket effect. You ablate one side of your target, that creates a plasma, launches a shock in the opposite direction, okay? And the setup is here. The X-ray probe comes in right to left. Target chamber is shown on the right. And this opens up quite a bit of different kinds of scientific research, from planetary science all the way out to high energy density physics and plasma physics. That's the emphasis. So a little bit on shock compression. So we combine the momentum, energy, and mass conservation equations, so-called the Rankine-Hugoniot equations, okay? And we find that a material will trace out a particular path. So here I show the principal Hugoniot. So a Hugoniot is a locus of all the possible thermodynamic states that are achievable behind a shock front. So if you send in a shock wave, okay, there will be some material that is at a particular high pressure, high temperature state on the Hugoniot, and behind the shock front, or excuse me, in front of the shock front, you are still at ambient condition, okay? So these two regions are called to be in local thermodynamic equilibrium, but at this interface, right, you are far from equilibrium in your material. So exploring phase transitions in this context allows you to look at not only equilibrium or local thermodynamic equilibrium, but also non-equilibrium components in your system. So the Hugoniot is not the path that the material takes, right? So for instance, here is the temperature pressure diagram for iron, and on here in purple is an example of a Hugoniot, and so there are particular high pressure states that one can access using shock compression and combined with ultra-fast X-ray probes to determine structure and other material properties. So here's a standard sort of cartoon. We have our laser drive, like I said, generates a plasma and blows off. Okay, Newton's third law launches a shock wave in the opposite direction, and then we probe. We use a suite of probes to tell us about how our material is transforming. So the new component here is that we're going to utilize X-rays in a new way. High fidelity temporal resolution is going to be the key. So we can collect diffraction, but we're also going to showcase today, or I'll also mention, some X-ray emission spectroscopy. So bringing into play new X-ray spectroscopy techniques that can be combined with shock compression. We also have sort of the standard workhorse, so a velocimetry technique that is coupled, measured in tandem with our newer X-ray diagnostics to tell us, to benchmark shock speed and particle speed of our material. Okay, so first material up is SiO2. So SiO2, quartz, fused silica, ubiquitous in our daily lives, important not only in industry, but also is the second most abundant material in the Earth's crust, undergoes a fundamental reconstructive transition going from 4 to 6-fold coordinated about 500 kilometers below your feet, but details the nature of this transition between, say, 4 to 6-fold coordination in SiO2 is actually poorly constrained. Now, SiO2 has been well studied in both the static compression community and the dynamic compression community, but for the first time, we'll be able to explore the phase transition kinetics of SiO2 transforming to high-pressure polymorph stishovite. We're going to look at nucleation time, grain size, grain growth, to pull out phase transition mechanism. How does it transform? Then we'll also look at a real rock former. We'll look at alpha quartz transforming to stishovite to actually give more context between what we find in the field at an impact site and what we can find in the laboratory. So trying to make a correlation there between the laboratory and the field. So it is essentially a pump probe experiment that we execute. Okay, so here I show a schematic of our setup. In the center, our sample cassette, so our SiO2 samples. Okay, we come in on the left-hand side here, I show in green the drive laser. The spot that is ablated on our sample and that actually aids the generation of the shock front is always larger than our X-ray probe, right? We send in our X-ray probe here is shown in pink, and you can see one indication in some of our experiments, we orient the starting material in a particular way so we can track, say, changes in texture, preferred orientation, or fabric as a function of shock compression. Downstream we have essentially area detectors. So this is going to collect the Bragg peaks or the slice, 2D slice through the Debye shear cones so that we can then integrate and identify what is the resultant high pressure phase. On the lower right side here, I just show little snapshots of different time delays. So the shock is launched in our sample. That shock front travels at a certain velocity. I select when I probe with the X-rays to see volume fraction shocked and unshocked, right? And that is then resolved in the downstream diffraction. Our samples are many. So the rep rate here of our drive laser is once every 7 minutes, okay? So to build up a kinetics data set, to look at time-resolved diffraction, I have to have many, many targets fabricated. So here's an example. This is, several millimeter by several millimeter. Hundreds of these targets have to be fabricated in advance for these experiments. I will mention that we do have a layer of plastic, I refer to as CH here, but there is a layer of plastic on the drive side. This helps to homogenize or make a more uniform shock as it enters our material. Smooth out any hot spots that may be present due to our drive laser. Okay. So the setup, here's a snapshot of what we have inside our sample chamber. So here's that little cassette of targets. It's several inches tall by, say, 10 inches long. Our drive laser comes in left to right. These are 3-inch optics that are used to focus the high energy laser down onto the target. And then downstream we have our CS pad, so-called Cornell Slack pixel array detectors. Okay, so this collects our diffraction. Okay, so what do we see here? This is an ambient condition fused silica pattern. So we should see no diffraction here. It's a glassy SiO2 material. Maybe we have some diffuse signal here. This is 2 theta increases left to right. This is a 0 time delay, so we should really see nothing. There's some blemishes from damage on the CS pads downstream. So now what happens when we launch the shock and I probe at a particular time delay? We see this beautiful diffraction, okay? It's fairly smooth. These peaks, I can then index based on position. I can index them as pure stishovite, okay? So we're seeing fused silica transformed to pure stishovite. This is at a time delay almost 12 nanoseconds, okay? So our shock front has pretty much traversed our entire sample about, okay? Moreover, we can say the nature of the diffraction here is that we're not getting much preferred orientation. I admit the azimuthal coverage here, so this direction of the diffraction, we don't have a lot of coverage, but we don't see anything obvious initially. And the peaks are fairly broad, right? It's sort of diffuse, so you might assume small-ish grain size, right? If we now integrate this pattern and look at a set of different pressures, so here, let me orient you. This is intensity as a function of 2 theta. I've clustered my pressures, so here's about 5 GPa, 7.5, 19, and 33, okay? And I've color-coded the different time delays. So traversing the entire sample is about purple, or 11.5 or so nanoseconds, and then earlier time delays are different rainbow colors. So let's pull this apart a little bit. Higher pressure, so 34, 20 GPa, we notice almost immediately we see our peaks corresponding, or that I've indexed to stishovite, they come up very, very quickly, so early time delays. And I see pretty much only crystalline. There's no superpositioning of any other features, so it's just crystalline material. And you could say, having some background in diffraction, the peaks are sort of broad, right? So the grain size is fairly small. For the lower pressure, 7.5 to 5 GPa, initially, early time delay, we see a superpositioning. So first, our diffuse signal from the ambient condition glass, it's compressed, right? So we see a shift in this diffuse signal, and then at later times, so red to pink, somewhere 9, 10 nanoseconds, we see now a superpositioning of the stishovite on or in tandem with the compressed diffuse signal. So this is very interesting. 2 different things going on here. The data quality are quite good. In fact, X-ray free electron laser based diffraction coupled with shock compression has really provided the first opportunity for shock physicists to perform Rietveld refinements on their data sets, right? So this is really revolutionary in that you can begin to pull out phase fraction information. And this is a very powerful technique. The next way in which we looked at our data is to assess the grain size. Now, we know the standard shear equation essentially relates peak width with the grain size. Here I used a modified approach that also includes some component accounting for the strain in our sample. Okay, so it's called a modified Warren-Averbach approach. But I'm able to essentially look at my diffraction peaks, pull out the peak width, and assess grain size. I can do this as a function of time and pressure and temperature. So here I do that. Grain size is a function of time. Each color-coded trace here is a different data set. And I fit a fairly simple approach, a very simple functional form to these data, wherein the grain size is proportional to time, okay? And there's a relationship here where the exponent of this functional form, this n, gives us information about the mechanism of transformation, okay? So the n, this exponent here, is something like 7. Now, if it were it is a reconstructive phase transition, but what is expected for reconstructive phase transition is that the time it takes to undergo this breaking and association of bonds is some long time scale. Moreover, it's likely diffusion mediated, right? And an exponent that would be associated with that is something like 3 to 4. But I cannot fit 3 or 4 or anything close to these data. I get something more like 7. And so 7 is associated with something like coalescence events or aggregation of nanocrystalline particles. Okay? So the grain size here is only something like 20, 25 nanometers. So very small particles of SiO2 are coalescing or aggregating, okay? And that's how this transition is taking place. So here's sort of a cartoon of what's happening behind the shock front. We start out with very small grains, and then very rapidly, say even just in a few nanoseconds, we're immediately blossoming into these slightly larger nanometer-sized grains. So this is on compression, right? The shock front has only made his way, let's see, is there a picture? No. Well, anyway, the shock front has only made its way through the entire material. But what happens on release? So now we're thinking in the context of a real impact scenario where you have compression and then release, and your material goes through both processes, okay? So here I show again on the left, intensity is a function of 2 theta. We still have our clusters of pressure here. The colored traces are the highest pressure that I just showed, but in gray and black, now we're looking at later time delays. The laser has turned off, okay, and we're starting to release from the upstream side. And what we see remarkably is that there's a diffuse feature that comes back almost immediately. Almost immediately, we are reverting back to our diffuse amorphous state. It takes a little bit longer. We hold on to our crystalline material a little longer before we get our diffuse pattern back, even at the highest pressure. Okay, and so here's an example of the path we take. So here's the fused silica hugonio. These are my peak pressure states that I achieve, and then upon release, the path that is followed in blue. But we see this amorphization. Moreover, we could collect recovered material, which we do, from some of our, so for instance, our highest, but we do have data down here, it's coming, but we collect from, say, our highest pressure state. So here, let me orient you. This is Q, or like you think of it as D-spacing, is a function of time. So we start out ambient condition. We shock compress to our maximum. So here we are compressing, and then on release, we sort of follow 2 different trends here. So the lower pressure set sort of comes back down to something that's more like our ambient condition 4-fold coordinated, but the higher pressure one does a sort of uptick. So could we be seeing 2 trends here? Could we be seeing a quenching in of a high density amorphous state? Perhaps. This also leads us to think about, in the real rock scenario at an impact site, we only pick up 2% by volume stishovite. A very small volume is actually crystalline stishovite. There's quite a bit of what's called diaplectic glass or shocked glass. So the pathway, how that shocked glass transforms, maybe this provides insight on that. Moreover, we could think about our data in a different way and talk about, instead of an equilibrium phase diagram that we think of commonly from a static compression diamond anvil cell community, we could think of a non-equilibrium phase diagram. In other words, now we have pressure, temperature, and time. So here I show our maximum pressure achieved and time, and I've sort of clustered out the different phase stability regions that I access, but now as a function of time. So this is really exciting because I can go back to the work of, say, Stoffler, Langenhorst, DeCarli, folks who've looked at recovered material, tried to establish from a shock metamorphism perspective a pressure mineralogy scale for impact sites. And we can now add this new component of time and think about what effect does that have, and maybe recast some of these shock stages in the context of when this diaplectic glass is forming, how stable it is as a function of peak pressure achieved. So this is very exciting on providing maybe some new constraints for some of these different shock stages. We also look at quartz, okay, so this is just a preliminary data set. Again, we have intensity as a function of 2 theta. Now I orient my single crystal quartz, such that I do not burn a hole with the Laue pattern, the bright spot of quartz, in the CS pad. So you'll see my gray traces here, so 0 time delay. We don't have any bright spots, right? So that's done on purpose. I don't expect to see anything. But now as a function, again, of the shock wave moving through my sample, and I probe at certain time delays, so that's the colored traces here, we see quite a few features develop. So first of all, we do see crystalline stishovite. We see peaks that form that can be indexed, once again, as stishovite. But we also see some superpositioning of broad features at the same time, at maybe earlier time delays, so maybe seeing an intermediate amorphization stage going from the quartz to the stishovite, maybe, right? Then on shock release, again, for a lower pressure, say 20 GPa, we see a diffuse signal come back. But again, at the higher pressure, so this is almost 50 GPa, we see the crystalline material hang on a little bit longer, as well as the superpositioning of the stishovite. So here's an example, or excuse me, diffuse material. So here's an example of a pattern we have at 8 nanoseconds. We also probably are seeing some of the quartz grains fracture and maybe rotate into satisfying the Bragg condition. Some of those overlap the stishovite peaks. So it's a much richer data set here with the quartz transitioning to stishovite. Okay. So that's the crust. We're going to move on and look at another component that is often in icy satellites and water-rich planets. We are going to look at structural transitions in water, in H2O. Now, water has a very complex phase diagram, and one could pursue a suite of different pressure temperature paths. So here's a phase diagram. Multiple structures are accessible by diamond anvil cell. Using a shock compression, you can traverse isotopes or principal hugonios and look at some other phases. In this experiment that I'll show, we're going to stay at fairly low pressures and temperatures, about 5 to 7 GPa. Again, the experiment is pump probe. Okay, so we have our package of liquid water that we start with. My little cell that I fabricate is here, so it's sandwiched between diamond and quartz, both of which are single crystal. So I should not see any polycrystalline evidence from them in the X-ray diffraction pattern. Our water will be diffuse, give a diffuse signal. Okay, same idea here. We send in our optical laser to drive the shock. We probe with the XFEL, with the X-ray free electron laser, and at certain time delays, I probe, collect that diffraction. Okay. These targets were extremely challenging to make. You can see in this little cutout, there's a meniscus of the water sample. This is shiny to your eyeball because there's a gold layer. So the gold layer will give diffraction, powder diffraction signal. I can use it as an internal pressure calibrant, okay? And that, we'll see that's advantageous. So the setup is shown here. Again, our sample stage is in the center of this image. CS pads are around. I want to draw your attention, this is a phase diagram, so temperature is a function of pressure. If I stayed on the principal hugonio, it would always be too hot, right? So I'd only see liquid. So we have to choose shock compression conditions that keep the temperature down. Okay, so we're going to do something called ramp compression, or extend out, stretch out the energy we deposit as a function of time over a longer period of time, such that we sort of slowly, a little more slowly push on our sample, okay, and then probe what phase transitions transpire. So here I show some of the raw data, so it's a little hard to see, but there is, our gold peaks are here, and there's a diffuse signal that develops. This is a shot now up to 6 GPa, 20 nanosecond delay or so, and you can see that there are some changes. There's some changes in the diffraction. It's hard to see in this particular image, but if we now look at integrated traces, it becomes slightly more clear. So here I show our X-ray only. We do have gold, so I do expect crystalline features there. Maybe a little bit of the diffuse signal seen. Now we march, as a function of time. So 7 nanoseconds, 11, 13, 17, 20. So over this period of time, the laser is on. I am pushing on my sample the whole time. And what we see is maybe at 7 nanoseconds, there's a tiny little shoulder. It's a little hard to tell. Tiny little shoulder pops up here, and there's some feature over here. Orange trace, we see a doublet emerge here. So one of those I know is the gold. The other one is a new feature, okay? And then there's something over here. This also is gold, which I can track. Green, unfortunately, they're superposed, so gold and what I'm calling as ice 7 is now overlapped. And then the top two traces, sorry about that. Top two traces have no gold, okay? So any diffraction I see is coming from my ice, okay? And again, we see a feature here and here. So these two new features that I see in the diffraction, I can index as ice 7. I can also look at static compression, high temperature data, and compare their lattice parameters, essentially their equation of state, and pull out a pressure. I can also do that from the gold. And there's remarkable overlap, okay? So here we're seeing both the gold and the ice 7 tell me something like 5 or so, 5 to 7 GPa. Now this is really interesting because earlier data sets, shock compression,
Can you just clarify why there was no gold in the top two?
I had removed it. I wanted to make sure that the features I was seeing was really not from any issue with the gold, to actually verify that it was the freezing of the liquid. So it was by choice. Dan Dolan and coworkers executed a set of nice compression experiments on very pure water, looking at the shock freezing of liquid water to a solid. And you can see that on the order of hundreds to thousands of nanoseconds, they see in a transmission, optical transmission geometry changes, okay, that would imply you're solidifying a material. But what is this material? Is it crystalline? Is it amorphous, a high density amorphous H2O? We didn't know. Moreover, is this really the time scale? Does it really take hundreds of nanoseconds to compress into a solid phase? Chances are no. Yeah.
Why do you have these negative peaks or whatever they are? Like
Oh, I'm sorry.
62?
Yeah, that's a great question. So there are breaks in the CS pad. So our detectors are actually mosaiced single crystal silicon chips, essentially. And there's no way to get around it. I could certainly put in a value here, a constant number, so there isn't this big break. But it's an artifact of the detector. Okay. Again, we can do Rietveld refinement. So I want to stress that is really a new feature. Diffraction has been collected at other laser facilities, but really the opportunity to execute Rietveld refinement is this new piece coming from an X-ray free electron laser-based diffraction experiment. So utilizing Rietveld refinement, I can pull out phase fraction. If I can pull out phase fraction, it means I can relate volume fraction of new phase as a function of time and apply some sort of very simple functional forms from classical nucleation theory to this phase fraction as a function of time. So here I'm showing this. This is the expression commonly referred to as a Jmac model, or the Johnson-Mel-Avrami-Kolmogorov model. Starting in the late 1930s, this was applied to melt quench experiments to look at the kinetics, okay, the kinetics of the phase transitions that were taking place. So here we're trying to apply this very simple functional form to the data that we're getting here on shock compression. And so here I show my best fit. The incubation time, or the time it takes to seed and grow a new ice 7 crystal, is something like 6 nanoseconds. That seems quite fast for a disorder to order transition, right? Moreover, this exponent, so it's often referred to as the Avrami exponent, is commonly tied to mechanism or transformation pathway. How is it transforming? Typically, a value of somewhere between 3 and 4 is associated with diffusion-based volumetric growth, right? So there's also some geometrical, yeah.
Sorry, can you clarify how you get a phase fraction when you have one crystalline phase?
Ah, that's a great point. So here, my trick, there are two ways. I've utilized the gold. The gold is a known volume of material, okay? So I have purposely used that in tandem with my volume fraction of unknown material to solve for the total phase fraction. In other words, it's a relative.
Gold with foil?
Is it a foil? It's a deposited. It's deposited. So there will be, if you're getting at a porosity issue, there is a little bit of porosity, but it's actually at these thicknesses
And
fairly negligible. I'm sorry, what?
And texture.
There is a little bit of texture. That's right. So that's included. You can incorporate texture components into the reed belt refinement. I didn't find that it was so pronounced with the gold at this deposition, but that is an issue for other deposited metals, absolutely. So we have this methodology that I've developed using this embedded layer, this gold layer, to pull out phase fraction of the crystalline ice. And I have this fit. And from the fit, I'm finding that the exponent is very small. This is unusual, okay? It's not common. And the mechanism that is proposed in a lot of the literature is something like it's one-dimensional sort of rods or pencil-like crystallites of I-70, perhaps. But this is a very qualitative sort of perspective, right? This is probably not right, but this is the best we can do in understanding how to frame our kinetics data in the context of classical nucleation theory. So it's a good first step. Is this absolutely the correct answer? I don't know yet. Okay, but this is where we're going. We have the opportunity now to use these methods developed in classical nucleation theory and apply to time-resolved, high-pressure, high-temperature shock compression data. Okay. So perhaps we can think about this in the context of icy satellites or icy planets in learning about their thermal structure, PT, pressure temperature stability regions. And again, I point out we're really only looking at a very low pressure here, maybe up to 5 to 7 GPa. So we're focusing more on icy satellites than any high pressure opportunities, certainly not superionic and the like. But this could provide some constraints. If we move on now, we'll go a little deeper into the Earth, into the mantle, we can talk about material that is an iron-bearing silicate. So here, we're going to transition a little bit, and we're going to think about deciphering seismic inhomogeneities in the Earth's mantle. Okay, we know that 40% by volume is Bridgmanite. And the iron in the crystalline material in the lower mantle, the nature of the iron, how spin transition in particular may affect physical properties, transport properties, thermal conduction, certainly the seismic velocities. These are all important components to understand and resolve. And we endeavored on an attempt to explore electronic transition in an iron-bearing silicate, so in this case an iron-bearing pyroxene, and structural transition. So can we divorce the onset of these two transitions, and what implications might that have for the Earth's mantle? Again, it's a pump probe technique, so we have our target in the middle. Our drive laser comes in on one side. Our X-ray free electron laser, this time in yellow. We do collect diffraction, right? So we have structural information, but now we also have a spectrometer, okay? And we're going to utilize X-ray emission spectroscopy. So I want to talk about that for just a moment. So if you look at the last unfilled electronic orbital, this is an electronic fine structure of that last orbital, wherein we're looking at the splitting, essentially the E-G to the T2G transition going from a high spin state to a low spin state. Okay, it's more energetically favorable at higher pressure to go into a low spin state. Now, if you try to examine this using a synchrotron-based technique, so I should just say, so here in this emission spectroscopy, we're really sensitive to oxidation and spin state. Okay, so there are other kinds of spectroscopy techniques we would want to test, to field, and those are not yet technically achievable. They're just, it's impossible to do. So this is one that we could do. So we looked at the spin transition in this material, and the typical, what you would look for, the typical pattern you would expect, say coming from synchrotron-based experience, is there's a K beta and a K beta prime. And when the transition takes place, the K beta prime peak actually disappears. Okay? And so we hope to see in our shock compression data some sort of K beta peak diminish or go away completely. Okay. So that's what we expect to see. Here's a picture of the spectrometer itself. It's several feet by several feet. Actually fits inside the target chamber. Okay. It's this von Hamos design, energy dispersive. Okay. And has been fielded on other experimental hutches also at LCLS to do the same kind of work. So here we are, iron-bearing silicate, so-called hypersthene, so it's essentially an iron-bearing pyroxene at ambient condition. I'm sorry, this is a little hard to see, but we have our pyroxene crystalline structure. I'm going to shock compress up to these conditions, about 40 GPa, 900 K. In the diffraction, I just see some compression. Okay, so about 17% compression. This is my shot or my compressed image. In the emission spectra, what do I see? So X-ray only is in blue, and then my shot. Okay, so they pretty much are superposed. If you look at the difference pattern, it's about the same. Okay, so we don't have a spin transition. We have compression, but no spin transition. This is at 10 nanoseconds and 40 GPa on the Hugonia. Yes, sir?
How do you know you have Fe3+ in the sample if the starting material is about?
So we did do chemical analysis. There are two sites that we were looking at, or that we had Fe2 and 3+. So that's a good point. It's mixed with this material. I can show you some of the compositional characterization if you'd like. Okay, so now we shock to a little higher pressure. Here we are at 80 GPa and 1700 K. So here's our ambient condition pattern. On shock compression, the diffraction shows some new features. Okay, here are some lineouts of those features, and here's the area detector. So these new features I can index as belonging to a Bridgmanite crystalline material. So I'm saying I see a structural transition take place. Okay, this is again at a 10 nanosecond delay. If we look at the emission, okay, I know it's a little bit hard to see, but the X-ray only is in blue, and you can still resolve your K beta prime in the blue, but in the red trace, it's a little less. In other words, and it's more pronounced if you look at the difference pattern here. In other words, we are going through a spin transition. So this is really remarkable. We have two different data sets that show structural transition and spin transition in the same shot. So the next obvious question would be to take the same kind of data set, but now at different time delays, to do exactly that divorcing of which comes first. Electronic transition followed by structural, or structural followed by electronic, right? So that's what's coming up next. So we just found out on Friday that we have more beam time allocated for later on. So that's the direction we want to go, right, is to actually do this experiment. Moreover, we want to go to higher pressures and temperatures, even push it into the melt bound and look at spin transition in a melt, okay? So just to show, okay, I know this is the magnesium end member, but just to give you an idea of where we are on the Hugonio, so we were somewhere 40 or so GPa, and then a little bit higher, approaching a megabar. Finally, the ability to use X-ray spectroscopy technique in an ultra-fast setting to explore differences in electronic versus structural transitions. Okay, and moving on to my most favorite and final part of the talk is the core. So we're going to go 6,000 kilometers below your feet. It is the most remote region of our planet, a very bizarre place. Pressure ranges here are something above 3 megabar. Temperatures as hot as the surface of the sun. Okay, so this is a really unique part of our planet. In particular, the inner core has some interesting properties as observed by seismic information. So there's an anisotropy, perhaps due to the alignment of HCP, or hexagonally close packed iron in the innermost inner core. Okay, and there's disagreement in the community experimentally as far as how that anisotropy, the compressional wave speed, travels 3 to 4% faster in the polar direction than in the equatorial direction. So one question to be posed here is, how did that come to be? What is the mechanism of that anisotropic development at the material scale? So here, the goal is to look at the evolution of texture, the evolution of strength, and include a high fidelity temporal component to this, because we are doing shock compression and we can look at the material time scale. Okay? And we're going to focus on 2 regions in this experiment. Lower pressure, where we can actually overlap with static compression strength data, and then we're going to push it as high as we can and go all the way up to try to achieve melt and just crisscross above and below that melt bound. So from a static compression perspective, radial X-ray diffraction affords us the opportunity to observe the maximum deviatoric strain by non-hydrostatically compressing our sample, and then probing perpendicular to the compression direction. Okay, this is going to set up an observation or a view of our Debye shear cones in its most, it'll be most non-hydrostatic, but access to the maximum waviness. If you were to unroll these circles or ellipses, they really will be, you'll see some distribution in D-spacing of the different crystalline planes or Bragg peaks in your sample, in your HCP. Okay, so my idea was to apply this to shock compression. So we executed this experiment in a diamond anvil cell to come up with a bound for the strength. And we found, not to go into too much detail, but we found that it was actually, so here's strength as a function of pressure, using something called a SING methodology, which has some underlying assumptions, but it's a rough bound, and we find that the strength is fairly low. Okay, it's like 8 GPa. This is at room temperature. Now at high pressure, or excuse me, at high temperature, we can do an extrapolation. We can estimate what the effect of temperature will be. Something takes the strength down to 1 or 2 GPa. That's really weak. Okay, so could that low strength be a possible to possibly encourage different kinds of dislocation flow or solid state flow inside the innermost inner core that then sets up this anisotropy? Perhaps. But best would be to make a simultaneous high pressure, high temperature measurement and look at strength. So we decide to do this using dynamic compression and adopting a schematic. Do I have one? No. Adopting an experimental approach where we basically combine the radial X-ray diffraction approach to the dynamic compression. I'm sorry I don't have a schematic of that. We do want to monitor starting mesoscale differences in our samples upon compression, okay, because that will really intimately affect the strength measurement or the texture evolution that we see in our sample. So just to say that we did that. We want to diagnose up to what strength, what is our resolution that we could achieve at the dynamic compression, with the dynamic compression experiment. So there's this Q factor that was used in the other study, essentially looking at magnitude of the deviatoric strain, and it's parameterized. This H is just a parameterization of lattice plane. So typically what happens is you measure your different lattice planes, you have your various Qs, your various magnitudes of deviatoric strain, you take some sort of average. But best is to have the end members here, so some value to bound the edges essentially of this parabolic fit, okay? So in our dynamic expression experiment, the dynamic compression experiment, we do have a good range, okay, of lattice parameters. And that means, moreover, the sensitivity that we need to get to is down to a Q of maybe 0.001. So a fairly low value. And the current sort of state of the art in terms of strength measurements in a static compression sense are at a pressure, combined pressure and temperature of something like 17 GPa and 4 to 600 K, something like that, okay? So we look at some of our calibrants to assess, do we have the resolution to make this measurement? The answer is yes, okay? I can resolve stresses in my dynamic compression experiment down to about, a little above, 0.001 Q. In other words, I have the resolution. If iron is really as weak as I predict it to be, 1 to 2 GPa, at inner core conditions, I should be able to resolve it with now in situ dynamic compression, high pressure, high temperature experiments. So here's an example. I'm not all the way up at the highest pressure point, but this is something like 140 GPa. Here is a movie, slices, snapshots of the diffraction, and you can see some distinct, so there's a BCC structure here that starts, and you immediately get the HCP triplet, and some changes in the preferred orientation as a function of time, okay? And all of these shots are executed at the same high pressure temperature condition, okay? So we can also track as a function of starting texture, starting fabric in our material to see how that evolves. So the exciting point here is we're poised, so I don't actually have the answer yet, but we are poised to make this measurement, to actually measure the strength of iron at these very high pressures and temperatures. Not all the way up to 3 megabar, but we can follow along the Hugonio up to that melt bound, and then on release as we look at melt and then resolidification. And the resolution is appropriate to actually make this measurement. So that's very exciting. So to conclude, in the final seconds, we've sort of taken a tour through the Earth, looking at time-resolved phase transition kinetics in materials that are important, not just for our planet, but other planets in general. We looked at fused silica transforming to stishovite, finding that we have this aggregation of these nanocrystalline particles that then grow, and then an amorphization or reversion to an amorphous, perhaps diaplectic glass on release, okay? The water shows shock freezing into ice 7, okay? And it's very fast, only say several nanoseconds to nucleate and grow, perhaps these elongated crystallites, perhaps, of ice 7. So that's really interesting. The iron-bearing perovskite shows, we think, mutual structural and electronic transition. Deciphering the onset of those two transitions is still to be determined, but the opportunity is there. And then finally with iron, we are poised at the point to look at the strength of iron on the Hugonio and follow texture evolution, and maybe add some more insight into how the anisotropy in our innermost inner core was established. And with that, I want to say this is a very exciting time in mineral physics and condensed matter. The the advent of the X-ray free electron laser to provide these ultra-fast X-ray probes coupled with any other external process is very exciting. So I encourage you to look. You can always certainly ask me for more details, but another call will go out for proposals in May for LCLS, and there's a lot of opportunity here. And with that, I'm happy to take your questions. Thank you.
Great, thank you very much. So let me just start. So
Yeah.
does the probe itself heat the sample?
Yes, so there is X-ray damage, which we monitor. So we can select a larger probe size, so say 50 to 80 microns, and that is a fairly safe size for our sample materials. We've tested down to as small as, say, 1 or 2 micron probe, and there we see almost immediate X-ray damage.
But does this mean the temperature is higher than the eugonio? I mean, for example.
Well, so we on purpose don't select such a tiny spot size. So always our spot sizes, we can record tens or hundreds of events in a row at the, say, 50 to 80 micron spot size, and we see no change in the diffraction. So then when we actually do pass the shock through the sample material, we know that there's no contribution from the X-ray with those parameters.
Yeah, it's very exciting, be able to combine with those different techniques to characterize things. And one of the things that I want to comment is on really the spectral work, because you're studying the perxing, right? From the traditional gas gun, we know there's a mixed phase region. So it's not really a very easy way to detecting the high pressure phase or the spin transition, because most of them we maybe see depends the percentage of the transformation, because in perxing we know it's about 100 GPa probably see pure perovskite. So the better experiment maybe we need to start as pre-synthesized perovskite.
I totally agree. No, that would be perfect. Yeah, we would love to try that.
Yeah.
Definitely.
It's very good.
Other questions? Dick?
Okay, for the silica glass,
Yeah.
you also see big hump. If you pair
Yeah.
that with glass spectra, diffraction spectra, do you see the coordination change?
So I have to be careful how I answer that, right? Because from diffraction pattern alone, I cannot tell you absolute coordination. I can look at the trend in the change of that diffuse pattern. If I had, let me phrase it a different way. If I had a better Q range, right, then I could actually do a Fourier transform and look at nearest neighbor and then maybe constrain that a little bit better. But I'm limited in my Q, which means I can track change in the peak position and maybe peak width of that diffuse feature as a function of pressure or time delay. I would hesitate to associate an absolute coordination. So I'm casting these data in the context of, we see a trend, which might mean a transition to a higher coordination, maybe 6-fold. But these data alone, I cannot actually say coordination. I would love to be able to. So perhaps other techniques could be applied to the shock recovered material that I'm saying might have a different D-spacing for that diffuse peak. So like Archimedes style measurement, except these to get a density, right? Except these are very, very small, like particles, the size of a pen tip. So executing an Archimedes style, like a sink float, we've thought of that. Another option might be you can entrain it in a gas, right? There's pycnometry. Am I saying that right? Anyway, there are other options to extract a density. So we're looking into that, but that would be great.
But if you talk about Q range, you try to resolve more second shock.
Yes,
third shock.
I would like
but
to.
At least you have a first shock diffraction peak, do you?
That's true. I do.
So,
I mean,
so
we do have that.
that by itself can be modeled for 6-4.
It could be. It could be. I've tried, and I received a little bit of pushback from the community. Maybe some of you in the audience. So I don't know. So that's why I want to be careful how I answer, right? So I know that it's good to identify the trend first, and we've tried. Yes, sir.
I have two
Victor.
technical questions.
Yes, please.
What's the time resolution on your X-ray emission measurements? It's the duration of a probe beam? Or?
Yes, so actually the emission process itself is much faster. So it's of the order, say, I want to say 120 femtoseconds. It's very short. Our probe is something like 60 femtoseconds. So we're still shorter than the emission lifetime. So again, I would categorize it as more of a snapshot, except it's coming from a volume of material that is perhaps multi-phase, right? So we have to be careful.
That's actually the second question.
Oh, yeah.
You always assign in your data like a pressure. So there's distribution of pressures over your sample. So
There is.
What's the error bar?
So we tackled, so the error, let's start for instance in the SiO2 data. We did have velocimetry that complemented the diffraction. So I can assess a pressure using an equation of state, say a thermally corrected equation of state, I think it actually might be phased, to pull out the pressure from the SiO2. But then I also have velocimetry, gives me a particle speed and a shock speed. And there's also a pressure that I can extract from that relationship. And they match fairly well. When I say fairly well, the uncertainty on the pressure I showed today for SiO2, 33 plus or minus 5, not so good, right? So in that plus or minus 5, which is pretty big, I'm encapsulating some of that gradient, okay? For some of the thinner samples, so that was for a material that's maybe 100 microns thick, so fairly thick. Some of the thinner materials, we can actually diagnose the pressure state a little better, hinging more on the velocimetry side, transit time, but there is a distribution, you're right.
Thank you.
So in the recovery for silica,
Yeah.
so you mentioned, I mean, we see in meteorites and in impact sites, you know, we do see high pressure phases.
Yes.
And the release there must be much longer than in the experiment. But
Yeah.
you had this time scale where it seemed like everything should amorphize at longer time.
Yeah.
So maybe this is a comment as opposed to a question, but maybe you have an answer to it. I know that when I talked to DeCarli about this sort of thing, he was very interested in scaling, you know, and he wanted to, you know, blow up some mountainsides and things, but it never really happened, you know. But
Right.
you know, there's a long way between a meteorite, a shock meteorite, or an impact crater, and your sample size.
That's
you
true.
know? And so, how do you deal with scaling in space and time? You know, when you want to compare with natural impact phenomena.
That's an excellent question, and it's a direction that we want to go. So part of the stepping stones here, we started with the simplest case, so the fused silica, SiO2. Then we went to crystalline, so quartz. Again, pure sample, single crystal, right? We also have data, which I did not show, on a natural sample. So the natural sample pulls in grain boundaries. It'll also pull in some porosity. So having some distribution in porosity in your sample will actually kick you off the Hugonio a little bit. It'll be a little hotter, right? And some work has been done on looking at how distribution of pore spaces in a natural rock actually changes the PT, pressure, temperature, time path that your material will take. So it could be that it's actually easier to quench in some of these materials that are seen in a natural setting, but actually using like the real rock scenario. So we're moving toward that way, but we want to understand the simplest case first, and then try to expand to real rocks, which I have tried to do. And the other aspect I think you might be touching upon here is the issue of strain rate. So in an impact scenario, in a bolide hitting a planetary body scenario, the strain rate here is actually different than what I'm showing you, and I'm sweeping it under the rug a little bit. But the scaling strain rate scenario for me, which is like 10 to the 8, 10 to the 9, versus gas gun, like DeCarli's work in recovery, 10 to the 5, 10 to the 6, versus dynamic DAC, which is what, 10 to the 2, something like that, versus truly static compression, right? There's a whole spectrum. And so looking at changes in crystalline structure as a function of pressure, temperature, time, and strain rate, that would be That would be where we learn more about how to effectively scale between the different regimes. That's an excellent point.
Yeah, my comment is just
Sorry.
it's really a multi-scale
Yes.
problem, and if you take your data, and probably this is ongoing anyway, and work it together with mesoscopic modeling and even macroscopic modeling, and try to span those length and time scales, probably a bigger picture comes out. I mean, some years, the labs are probably doing this, but anyway, I mean, I know there was a big project some years ago at Caltech to try to do that on some simple materials, but it took a lot of people years, to get working together.
Sure.
But it's a hard thing to do because you take people from different fields and they have to.
No, that's an excellent, that's definitely, the mesoscale effect is definitely a very important piece.
The other questions?
I do have
Yeah.
one general question.
Yeah.
So you showed some of the very nice data that I did really get a sense in terms of pressure, space, and where you're going eventually with this kind of laser. What's the maximum shock pressure you can get to?
Right. So I would argue that in a steady shock scenario, we can achieve 250 GPa, so 2.5 megabar, with the current setup. Now, I've been told by management at LCLS there's an upgrade planned, okay? So in about a year, we'll have 2 more arms. So I always show these 2 beams coming in to ablate. We'll have a total of 4. So it'll effectively double the laser intensity on target. So the idea is then we could achieve maybe, it's not quite a linear trend, but say 4 megabar with ease. Mind you, there are, one needs to be careful that you don't just increase pressure and issues of laser stability, right? Because I probe as a function of time. But if shot to shot, and all my targets are different, right? Every single target, I characterize them such that I try to have them be identical. But technically, every single one is different, right? So jitter in the drive, if I'm taking 1 nanosecond, 2 nanosecond, 3 nanosecond, etc., right, is very important to me. So that's not part of what I covered today, but that will need to be considered as the facility upgrades. But the idea would be to have up to 4 megabar.
But the other thing is if you stay on the agonio, then everything will be melted.
That's true.
But if you do the ramp compression.
That's right.
Yeah.
That's right. So pulse shaping capability is also a major emphasis as well, to have exactly that. Oh, yeah.
So you talk about using plastic nucleation in growth theory.
Yes.
Which always assumes that you're going to heat that. And especially since you were talking about not very thermally conducting materials, you might have better agreement if you're thinking about like your heat reservoir being like localized due to poor thermal diffusivity. Is that something that you considered?
It's not actually. So the application of the data to this Jmac model or classical nucleation approach, functional form, is really in its infancy, and I'm looking into ways to take that what's been described as a phenomenological equilibrium expression to something where I am looking at a dynamic process. So components of it are very much non-equilibrium. So there is a difference there. I agree. That's a really good suggestion. But I admit that that's a difference. Yeah. Thank you.
Let's thank Arianna again. Thanks for going with this talk. So if you have a quick question and you're not on the schedule, you feel free to come up right now.